I would like to thank the organizers for this very nice opportunity. Today I will talk about dimensionality reduction techniques for global optimization. This work is joint with my postdoc Estelle Massart and my PhD student Adilet Otemissov, who has very recently and successfully completed his PhD studies. We are interested in solving a general objective function f that's continuous, possibly non-convex and possibly black box, over a domain that will either be the whole of Rn here or a box, and we are worried about the poor scalability of current methods. We would like to consider the use of random embeddings for reducing the dimensionality of these problems. So we would like to replace minimizing f of x with minimizing f of ay, where A is a Gaussian matrix that projects the vector x from the high dimensional space R capital D to a smaller dimensional space R little d. And we would then like to solve this reduced problem, and we are willing to allow more than one random embedding if needed. We were inspired in this work by the paper of Wang and De Freitas that looks at using random embeddings in the context of Bayesian optimization. We would like to propose a general framework here that moves away from just allowing Bayesian optimization to be used for solving the subproblem. When would such a framework be useful? Under the following additional assumption on f, that it has low effective dimensionality, namely it only varies along a possibly unknown low dimensional subspace of dimension, say, dE, some small dimension dE. And it would be useful to have in your mind this extended, translated sinusoidal curve, because it's a very good illustration of this special structure. You can see that this function is only varying along this direction, but it's constant along directions orthogonal to it. And so you can see that there are lines of minimizers. And so to just find a global minimizer on this line, if you try to hit it with a random line, to try to intersect it with a random line, the line of global minimizers with the random line will intersect with probability 1, provided there are no constraints. And so, without knowing the subspace, but knowing its dimension or an upper bound on it, you can project and solve this reduced problem and have a very high probability, in fact, probability 1, of finding a global minimizer. And that's why this particular structure is of interest in this context. Is this structure relevant to applications? Indeed, such a structure can be found in many practical problems that rely on a model that is over-parameterized. Very often, users over-specify models, like in neural networks or climate modeling. And so we expect that these models will be insensitive to changes in some of the parameters. If these changes, these insensitivities are with respect, are linear in the parameters, then this framework applies. So what can we say in this context? Well, assuming that our original problem is unconstrained and that it has this special structure of low effective dimensionality, even if we don't know the exact subspace, we propose to then rephrase it as a reduced problem through a Gaussian matrix A that goes from, instead of R big D, to R little d. But we are going to look at whether we could constrain this problem. If we have no constraints in the reduced problem, when we solve the reduced problem with probability 1, we will find a point y star that, if we then project back into the R big D, will give us a global minimizer of the original problem. However, for many practical purposes, it is very important to have a box domain, such as if you want to perform a branch and bound. So we would like to look at how could we choose this box domain to guarantee that it contains a minimizer, a corresponding minimizer of the original problem. And our work assumes that the random projections are with dimension little d, that is an upper bound on dE. So we assume we know dE, but we don't know the orientation of the effective subspace. We were then able to characterize exactly the minimizers in the reduced space in terms of properties of the minimizers in the original space, and to characterize them probabilistically in terms of an inverse chi-square distribution, which then allows us to decide the size of the domain in the Y space. In particular, this probability of success of the reduced problem in containing a corresponding minimizer of the original problem, this probability of success, we showed it to be bounded by quantities that are independent on the ambient dimension. So indeed, this optimization, reducing to this optimization question in the Y space, can be done, and it only depends on the effective dimension, dE, and on the dimension of the random embedding little d. So this would be very efficient for in terms of scalability of these methods. So what we propose then is that, assuming you know dE and being able to choose d to be equal to dE or a bit larger, and setting the size of the box in the Y domain delta based on our theoretical considerations, then you choose a random projection, and then you solve this reduced problem over a box domain in RD, and then project back into the original space. Very simple framework. One random projection, assuming F has this special structure, but not knowing the exact structure except its dimension. Because our original problem is unconstrained, and because of the properties of these special functions, it turns out that one random embedding is enough to obtain our original solution with high probability. I would like to mention that this corresponds also to a phenomenon that was noticed in neural networks, for example, where people noticed that just one random projection of the parameters of the network is enough. If you solve that, if you optimize that, train that, those parameters, is enough to give you a good solution of the original problem. So we were able to theoretically explain this phenomenon for functions that have this low effective dimensionality, which is very much a structure that's conjectured for neural networks. I would like to now exemplify numerically this simple framework. So we created functions with low effective dimensionality by taking 19 global optimization problems from standard test sets, adding fake dimensions. These 19 problems are small scale. We added fake dimensions, we added zeros with big D, sorry, not little n, 10, 100, 1,000. And then we performed the rotation of coordinates so that we do not always have the effective subspace aligned with the coordinate axis. And then we compared different global solvers, not with each other, but on their own, in a framework where either we apply the global solver by itself to the problem, to the larger dimensional problem, or to versus using our REGO framework, we randomly project once, and then we solve with that respective global solver in the subspace, and then go back through the random projection to the original space. So when we solve with direct, what we notice here, we have on the horizontal axis the big D dimension of the problems, and on the vertical axis the percentage of problems solved. You can see that in the no embedding framework, where you solve the problems directly, the probability of success goes down dramatically. However, the probability of success of finding a solution of the original problem stays essentially constant for the REGO framework, independent of the growing dimension of the ambient space. This is in line with our theoretical findings that this probability of success does not depend on big D, only on the low effective dimensionality and on the dimension of the embedded subspace. Similarly, we look here at function evaluations and CPTU time, and we see growth for the no embedding framework and essentially constant for the random projection framework. With Baron, we see similar behavior here and here. This just looks at kind of local solver properties in Baron. But for guaranteed global optimality, we have this plot and then the CPU plot here. And we see a similar type of behavior. For multi-start nitro, the success probability is very high for the no embedding framework. However, we can see the similar behavior of time and function evaluations growing with the problem dimension for the no embedding multi-start nitro compared to the behavior for the randomly projected framework. How about if we have constraints in the original problem? So we are talking here just about box constraints. Assume without loss of generality that we are in -1, 1, so a box centered around the origin. Then we transform the problem when we project it into a problem that is linearly constrained in the reduced subspace Y, in Y. So now we solve with respect to Y, but we have big D constraints, linear constraints in Y. We were able in this case to again quantify our the properties of the reduced minimizer Y in a probabilistic sense and to bound the probability of success of this reduced problem. So when does the solution of this problem correspond to solutions of the original problem? What we found, however, because of the constraints here, that of course now this probability of success, this lower bound on the probability of success depends on big D. However, in the special case where we just draw the random subspaces at the origin, and when the effective subspace is aligned with the coordinate axis, we were able to establish that this probability of success is independent, depends only polynomially, not exponentially, in big D. So there is some polynomial complexity here for the special structure functions in some specific instances. That's where we were able to show them. It's clear that this probability depends on big D of success. You can see it in the numerical experiments. And we only were able to obtain polynomial complexity in this special case of the low effective dimensionality. Here, I would like to note that we allow a translation of the random subspace. As we will see, this will be beneficial. And because of the fact that the probability of success now of the reduced problem depends on big D, what we need to do is to draw multiple random embeddings. So it will not be sufficient to do just one random projection, but we have to do multiple to increase the chance of our success. And this is why this P will come in as useful. Now, if you think about this idea of using random projections, this has been used in global optimization because people have been doing uniform sampling, random sampling to solve the problem, random searches along lines to solve global optimization problems. And so doing random projections and repeated random projections can be viewed as a multidimensional version of random search. Indeed, in this context, we were able to think of these frameworks of random projections where we allow either unconstrained problems or constrained over a box and multiple random embeddings. We were able to think about this for general objectives as well, not just for special structure. In particular, we were able to quantify the probability of success of a reduced problem in this multidimensional version of random search. So what we say is that given A, 1A, random A, we would like to quantify the probability that when I draw this random A, so I draw this random linear or affine subspace at P, so I have a point P, and then I draw my random subspace there. You can see here this red line. I want to know the probability that this line will intersect an epsilon ball B of a minimizer, a global minimizer X star of the original problem. What is this probability? Can I bound it? What is my success probability? And what we saw is that we could translate this question into a question that stochastic geometers have already answered for us. Namely, we can view this ball here as together with the point P generating a circular cone that's fixed and deterministic. And then we can view our random subspace based at this vertex P as a random cone, as a degenerate random cone. And so we can ask this question of what is the probability that a random cone and a fixed cone will share a ray, like in this picture. If they share a ray, then our reduced problem is successful. And so we use these techniques to bound this probability, and we found here a bound that now, of course, depends on big D. We have no special structure here, no hope of getting something really nice. However, this bound is better than uniform sampling when, for example, the minimizer is close to the center of the domain. And these bounds here can be used also to guarantee a framework for the case when we do not know the E. So in that case, we can still do these random embeddings and keep growing little d until we hit the E if F has this special structure. So indeed, we have this general algorithmic framework here where we can choose random subspaces of varying dimensions, little dk, Gaussian random subspaces. And then we solve this reduced problem that could be, depending on the problem, either completely unconstrained or constrained to be in a box. So this applies to the constrained over a box special structure or general objectives over box or over Rn. And then we have our next main iterate xk that's generated by yk and our anchor point pk plus 1. Then we choose another base point pk and draw another random subspace and solve a reduced problem again and again. Now, this pk allows us to be adaptive in our algorithm. So pk could be, for example, the best point found so far in terms of best function value for f, or it can be a fixed point, or a random choice is also allowed. So for example, if the algorithm is stuck, you can just draw a random p and this framework will still hold. If you know that f has special structure and you happen to know the E, then your dimension of the random subspace could be chosen to be constant and just an overestimate of the E. We can guarantee convergence of this framework, both for special structure and for general objectives, assuming that f is Lipschitz continuous and that each subproblem is solved to global optimality slightly lesser than the accuracy desired in the original problem, and a very diverse set of choices of the anchor points pk. Then we can show that with probability 1, our solutions of the reduced subproblems projected back into the original space will converge, will belong to the an epsilon ball of a global minimizer x star with probability 1. This proof crucially relies on the probability of success that we derived for each of the reduced subproblems, both in the general objective case and in the special structure case of low effective dimensionality. We also have some rates of convergence. Some numerical experiments very briefly. For the case when, again, we have this low effective dimensionality, we assume we know the E, and we slightly choose it the same or slightly overestimate it in the random projections. We are going to do multiple random projections, and either we are going to draw the subspace always at the origin, or adaptively in these X-REGO frameworks where we move the random subspace to the best point found so far. And these are performance profiles that again compare various global solvers with no embeddings. We see that for small problems, the no embedding framework wins. The no embedding approach wins. So just applying the global solver. However, when the dimension of the problem is large enough, we start seeing some gains for using random projections. Even more so with Baron, you can see here that for 1,000, our random projections wins over no embedding Baron. For Nitro, we even tried using a local solver so that instead of solving the problem in each subspace to just local, to global optimality, we solve it to local optimality, we move to the best point found so far, then draw another random subspace. And what we noticed is that indeed sometimes we get stuck. However, then we can just choose a random p anchor point and just start from there. And again, we see that, for example, in this plot, when the dimension is 1,000, these performance profiles here in orange and green, they correspond to local adaptive framework or fixed random framework, but again with local nitro solver, and they beat the multi-start global nitro of no embedding, and they also beat, in terms of success probability and evaluation counts, they beat the global solvers in the subproblems. This local approach is, of course, not covered by our theory. However, it is very encouraging numerically. And I will end here. We have developed this general framework and studied random embeddings for special structure and for general objectives, and try to quantify both theoretical and numerical properties. Thank you for your attention.